Alright, hey folks, I want to redo the video about celestial navigation here because I had some hang-ups in the last one, and that might have left some people a little confused as to some aspects of how to do the plotting on the map aspect of things, and so want to just redo it to go through some additional plotting procedures and maybe hopefully make it a little more clear. So this first video, it's going to be a couple videos. The first one here is we're just going to obtain all of our data. We're going to assume just an evening star site, and we'll get all our data together, and we will, if you watched the previous video, you saw this site reduction calculator here. We'll still use this here just for ease of just for easing people into this thing, but I actually will make another video about how to do the actual site reduction using a scientific calculator. It's actually pretty easy. And then I'll also show you, crazy me, I actually did find what was called the F-TAFU, which is the German site reduction tables that were used during the war. So I have those actually printed off. I could show you those in a video. But just for starters, we can use this website here, which reduces your site down and gives you the information you need, and then all you have to do is just plot it. So much easier. So I will do plotting on paper in the next video, so you can see that. The Germans actually did their site reduction on graph paper, and so I will actually do it. I'll do it the same way, using the same sort of annotations and style that they used. And it will be hopefully pretty clear. We'll do 2 stars. The intersection of the lines of position, of course, will give you your fix. But just for demonstration purposes, I did put our familiar U-boat icon here as if we plotted our way out into the North Sea. And I actually just for demonstration purposes, this is our actual position here. So you'll see I obtained when I did the quote-unquote sextant readings, those correspond to this location here. We don't know that this is our location, of course, but the sextant readings are, of course, because this is where we actually are. The heights that we get from the sextant of the stars that we shot will correspond to this location here. But we think we're here. We're going to use this as what's called our AP, or our assumed position. So for starters, there's a few steps we need to do, and if you watched the previous video, you know this may be familiar already. But so what we need to do is first of all, we need to know what day it is, and we will use November 16th, 1939. I showed these before. This is the Nautical Almanac for 1939 that was created by a Silent Hunter player on Subsim. All the data in here is correct, but just for review purposes or for new people, a few things, a piece of information here that are crucial. So you've got obviously the days here, right? You got the month for November 16th, 1939. Sun and Aries GHA. GHA stands for Greenwich Hour Angle. So what you're pulling from the Nautical Almanac here is actually what's called the GP, or the geographic position of whatever body we're viewing. The geographic position is basically just if you were to draw a line straight down from that star or the sun or whatever you're viewing, straight down into the Earth, that point at which that line intersects the surface of the Earth is the geographic position. Basically, if you were to look straight up 90 degrees, straight up in the air, and see that object right 90 degrees above you, you would be on that object's geographic position. This information is giving you the geographic position. It's actually one of the corners in the spherical triangle that we need to solve to do celestial navigation. Okay, so since we're doing star sites, there's 2 pieces of information we need. We need the GHA of Aries, which is a fictional point, essentially a fictional point of reference out in space. It is a part of the spherical trigonometry that we need. To that, we need to add the sidereal hour angle SHA, which is the essentially the angle from the point of Aries to the body, as part of the spherical triangle. We need those 2 pieces of information immediately to get the what we will call the GHA, okay, the Greenwich hour angle, which is essentially, it's an angle, it's similar to longitude, but it's measured from Greenwich westward. So let's just assume that, here's our prime meridian here. It's measured this way and then around. Okay, so if you're standing facing, at Greenwich and you go westward, you just go all the way around the Earth. That's how GHA works. It doesn't work like so and so many degrees west and so many degrees east. It's just one direction all the way around the Earth. So GHA, that's why you see some of these GHAs are greater than 180 degrees. It's because those are actually east angles, if you want to think of it that way, east longitudes, because they go past 180 degrees. Okay, so we're always adding. That's what we know here. So the first thing we need to get in the website, we need a few pieces of information. We need the Greenwich hour angle. We need the declination. The declination, we know Greenwich hour angle is essentially the longitude if you think of the geographic position of the body. GHA is longitude. Declination is its latitude. That is where north or south of the equator, where that geographic position is located. Okay, so longitude of the body, declination of the body. Okay, where it's shining onto the Earth essentially. So those are the two pieces of information we need from the nautical almanac. So we'll get those now. We need to interpolate if we're using an hour that's using a time that's not exactly on the hour. We need to interpolate here. For stars, these move, actually. This point moves, if you want to think of it that way, or the reference point. As the Earth is turning, the reference point moves actually 15.0411 degrees. Okay, so as the Earth obviously rotates 360 degrees in 24 hours. If you do the division, that comes out to 15 degrees an hour ish. That works for the sun, straight on 15 pretty much, but for the point of Aries, it's actually a little more than that. It's 15.04. So we take that into account. So the first thing we need to get is the GHA of Aries, okay? And we need to do it at the time that we sighted. And our sight was actually done 0630. And so we need to, first of all, find 06 on the 16th, which is here. We read across 144 degrees, 24.7 minutes. That's the GHA of Aries. But it's not at 06, it's at 0630. So how do we figure that out? Well, it's easy. Typically, you would just take, 30 minutes divided by 60, right? 0.5 times 15.0411, or just 04. That's the increment of change per hour. And so what you're doing is you're interpolating. So 7.5 degrees, we need to add that to the 0600 figure of 144 plus 144 point. So we need to enter it in as a degree, 2442. That's 24.7. Now you need to convert that into a decimal figure, because we're going to work in decimals here. Okay. All right, so that gives us this. Now we need to add this sidereal hour angle of the body we're looking at. The first body we want to do is Arcturus. We sighted Arcturus at 0630 with this second reading here. The next one is Regulus. We'll do that second. All right, so Arcturus, we need to go in here, find it here. There it is. The sidereal hour angle is 146 degrees, 47.7 minutes. So we add that to our number. So we say plus 146.4742, because that's 0.7. That's 42 divided by 60 is 0.7. Convert that to decimals, equals, 298.7 is our 0.72 is our GHA for purposes of entering in here. Now what this computer will do is, what this website will do is, it will subtract, it will add our latitude, or excuse me, our longitude as well. We don't have to do that. So for this gets us the answer we need for the website. So, but since this is in decimal degrees, we need to press DMS. You need to understand how to do that if you're going to do this. You need to convert from degrees to decimals and back again. So the way you read this is 298 degrees, 43 minutes, 43.6. That's closest to 36. 43.6 minutes. So we enter that into our website here. Okay. That's the Greenwich hour angle, 298, 46, 43.6. 298, 43.6. Okay, we got that one now. Now we need the declination. The declination of a star, the declination of the sun changes frequently because the sun is relatively close to the Earth, whereas these stars are an infinite distance away from the Earth. The declination does not change, so therefore there is no times listed for the sidereal hour angle or the declination per star. There's just a figure that covers 3 days. Okay, so that's helpful to know. So Arcturus, the declination is 19 degrees 27.8 minutes north. All right, think of that as the latitude of the body, 19 27.8. So we enter that in, 19 27.8, and it is north. Okay, now we enter our assumed position in. Well, we need to derive that. So the easiest way to do that, since we're using this Google Maps, is to simply click. Oops, this is our assumed position here. Click on it. All right, and then we just highlight the latitude, copy, paste it into here, click DMS. That gives us the degree figure, 54 degrees, let's just say 31 minutes. 54, that's latitude, 54, 31, it's north. And then the longitude figure, we do the same thing. We copy, paste it in, hit DMS, that gives us 3 degrees, 32.8 minutes, right? 3 degrees, 32.8 minutes. 32.8. And that's east. Okay, so that's good. So we're set. Here, now we need to enter in the observed altitude. None of this matters because I would be giving you your adjusted sextant reading in this. You don't have to do all of this stuff. This is obviously if you're doing it in real life. Observed altitude, that's given to you. That's 34. So we're doing Arcturus first. 34 degrees, 11.5 minutes. 34, 11.5. Okay, now we reduce the site. That means give us our computed altitude and our azimuth, and we're going to write those down. All right, so we reduce the site, boom, like that. And then I'm going to take my handy dandy pencil and I'm going to just come over here and jot down 34 degrees and 18.1 minutes. That's the computed altitude, HC. The azimuth is 105 degrees. You can just round it down to the nearest degree. Okay. So now what we need to do, there's one more step we have to do, and you'll see why we do this when we actually do the plotting on paper. So we need to get what's known as the intercept. That's the difference in the computed altitude between what we measured and what it actually is. There's obviously a difference because we're not assuming a position. We're not using an assumed position that's right on our location. So there's obviously going to be a difference. Okay. So what do we do? So let's just make a note. For this site, we'll say HC equals 34 degrees, 18.1 minutes. Okay, right? And then what we do is we actually do subtraction. We subtract HO, which is the observed altitude, from HC. And and how you always take HO minus HC. And when HO is a larger angle than HC, that means that you're actually closer to the body than you thought you were, which makes sense if you think about this. If you think about it in terms of range finding through the scope in Wolfpack, the higher the angle you measure of the mast height, the closer you are. It's just very easy to reason your way through that. Right? So we can do this math like this. We say 34.113. That's 34 degrees, 11.5 minutes entered in degrees. We have to convert it to decimals like this. And then we say minus, and then we enter the 34.181. 34.1806 is 0.1. Convert it, equals, and now we go back to degrees. Okay, so the offset is a minus away. You'll see what that means in a second. 6.6 minutes. So minus 6.6 minutes. That actually equals 6 minus 6.6 nautical miles, because in a nautical chart, 1 minute of latitude anyway, 1 minute of latitude equals one nautical mile. They keep it simple, okay? So our offset is minus 6.6 nautical miles, okay? And the azimuth is 105 degrees. So we need to know that too. So 105 degrees, okay? So that's that. Now we'll do the same thing for Regulus. We have our observed, just assuming the same time. It's not always in real life. You're obviously not, an octopus with 2 sextants and taking a reading of 2 bodies at the same time, right? So you're going to have a difference in time. So you need to recompute. So we'll go through the computation of GHA again, just to show you, which you would have to do in real life, because you don't, you're not doing 2 simultaneous sites, and seconds and minutes really do matter in this quite a bit. So same thing. So we know it's at 0.630 halfway. So we take our increment, which we always know is 15.0411. Let's just do divided by 2 because we know 30 minutes. Okay, plus, and we find 0.6144.2442. Convert that. Plus, now we find Regulus. We go down here, there's Regulus right there. We find the SHA of 208.4236. That's 0.6. Okay, convert that. Equals, okay, now you can see we're over 360, so we minus 360. Alright, and then we convert that to degrees by hitting DMS. Alright, so our GHA is actually 0 degrees 38.5 minutes. So we enter that in. Let's reset this. Should have made a note of my latitude. We'll have to recalculate that. Or no, sorry, I have it noted here. So we have 38, so 0 degrees and 38.5 minutes. Okay, now we need to get the declination, which is right next to it, right here. Regulus, 12 degrees, 15.6 minutes. 12 degrees, 15.6 minutes. That is north again, and then we enter our 5431 north, and then longitude is 332.8, and that is east. Okay, we reduce this. We need to put the observed altitude in. Which in our case is 47.439. Okay, and then we reduce the site. There we go. Okay. For some reason it didn't give me the intercept. I'm not entirely sure why. That's odd, but anyway, it doesn't matter. We just make a note of our computed altitude, which is 47. So HC equals 47 degrees. Degrees. 36.9 minutes. Okay, and then the offset, we do the math. We say our observed was 47.4354, 43.9, minus 47.3654. There equals that. We convert that. It's actually 7 minutes or 7 miles toward plus. So plus 7 minutes, which equals 7 nautical miles. Okay, at an azimuth of 186. 186 degrees. Okay, so that's this is the information right here. This this in bold is what we need. That's what we need to plot. That's what we're going to take to the plotting table, essentially, is this, to figure out this this, and this are what we're taking. We need to know where to plot from, okay, and then we need to know what our offset, our intercepts are, and our azimuth. Okay. So real quick, let me just jot down that our assumed position is 54 degrees 31 minutes north and 3 degrees 32.8 minutes east. All right, so we'll need that in the next video. Okay, so this is the simplified way of doing it. Probably doesn't seem simple now, but this is the site reduction site is bar none much easier than doing it by by way of a calculator or by the old-fashioned way of doing tables. It's also an interesting exercise to do that, but you don't necessarily have to do that when you have a site like this to give you the values. Okay, so so the way we're going to do this is in the next video I'm going to show you actually how to plot the intercepts, plot the lines of position rather, and then what we're going to do is we're going to do a little trick, because since the way this map works and what way a real map works is real maps are Mercator projections. They're not a flat Earth like say like a I'm guessing Wolfpack is this way, and maybe like Silent Hunter 3. There's just a flat Earth. Okay, there are no converging lines of longitude. Obviously, in real life, when you're at the equator, a minute of latitude equals a minute of longitude. You think of it as like a square. But the further north you get, say like if you're at the North Pole, for example, you can change your latitude by way of steps. You change a few steps or whatever, walking around in a tight circle, and you've just gone 380 degrees, right? Because the longitude lines have converged to nothing up at the pole. Okay, so you can see where a change like this, 178 miles, here is going to cross more lines of longitude, okay, than down here. Okay, it's you're gonna because the further north you go or the further south you go from the equator, the longitude lines converge. All right, so since we're doing our plotting on a piece of graph paper, which is essentially a flat Earth scenario, you need to do a little math trick with plotting, very easy, to convert that lateral distance to what it would actually be, and then we'll show you how to do that, and then we'll transfer that to the map. Okay, and then hopefully we're close to our actual position, which is here. All right, so we'll see that in the next video. So bear with me here. I will be on in a second.